All right, special relativity continued here, and we're looking at simultaneity. Simultaneity would mean, the simple idea that the concept of whether or not two things happened at the same time or not. And unfortunately, we're going to mess around with that a bit. Apparently, that is actually a relative concept. I'm going to show you how and why and whatever. So, special relativity describes the strange consequences of the fact that the speed of light, of course, is always this 300 million meters per second, regardless of your motion relative to the light source or its velocity relative to you, and so on, right? So if you're inspecting light, you're always going to see it going at light speed, not the train's velocity plus the velocity of the light, and so on, right? And an even harder to accept simple property, even harder to accept than that is the crazy effects it has, right? And so all the weird things we're going to learn are all consequences that follow from noticing light's strange properties. All right, so we're going to look at many things today. The idea of, or the seemingly obvious idea that's not actually a thing. The idea that two things can be considered at the same time, and that's a fundamental thing that everybody would agree on, basically. Not true, and we're going to look at effects on time and length and mass and so on. So I already gave those spoiler alerts, so we're good to go. So before we get to the simultaneity stuff here, picture a strange consequence here: a photon torpedo fired at a spaceship that's fleeing at almost the speed of light. Right? So a photon torpedo fired at a ship that's flying at almost the speed of light. So basically something that's going the speed of light fired at something that's going almost the speed of light, right? So the person that fired the photon sees it take a long time for it to get to the ship and destroy it, right? Because the ship's going really fast, right? So that's what that person sees. The passengers in the ship would see the photon torpedo, the photons coming towards them at light speed, therefore would see it hit them and destroy them very quickly. So which is true? Well, did the ship get destroyed right away or after a long time? So my job here is to help you understand and accept that the answer is yes. Both observations are what these observers would see. It turns out that because these observers are not, at rest relative to one another, and they're not both in the same state of motion relative to the event that we're observing, and so on, that the observations are different. An Earth observer would see the photon torpedo going away from Earth at light speed, and the ship going away at almost light speed, and so the time it would take would be a long time, right? An observer on the ship, of course, would see the photons traveling at light speed because it's literally light, and everything. Experiments show that all light is observed to be going light speed, period, no exceptions. And so the time observed for the ship would be very small. Okay, although these two observations seem to contradict each other, they are both correct. They are what the observers would experience. Okay, so you can see how this is going to lead into simultaneity being a non-existent actual concept too, right? So, ideally you think of the ship, they should both observe the ship being destroyed at the same time, right? But one says it took a long time, one says it didn't, and so on. So in a more extreme example, you could imagine the ship traveling at light speed itself or faster, right? So a problem occurs with this one because the person that fired the photon would see it never getting to the ship and destroying it. Passengers on the ship would see the photons coming towards them at light speed, and so it would hit them and destroy them very quickly. And so, a ship can't be destroyed and not destroyed. That is, of course, impossible. So we can't say, oh yeah, that's what both people see. So, which turns out to be, you can think about this. This would just, philosophically, right? The philosophy of this would be, okay, well, since that can't happen, then the ship can't go at light speed or faster, because then this would be a consequence of that, which is impossible, right? So it's one of the ways you could reason that nothing can travel at the speed of light or faster. Okay? The speed of light is the ultimate speed limit for anything. Nothing can travel faster than the speed of light. And it's impossible, really, for a spaceship to end up going even the speed of light. Okay? And we'll see more things to do with that later on. Starting with some now too here, but there's more that I'm thinking of to do with mass and so on for later. Right, so other ways to show that nothing can go faster than the speed of light. We're going to watch this guy here. So give me a second here.
E equals mc squared may be the most famous equation in the world. But what you might not know is that it isn't the whole story. It just describes objects that have mass and that aren't moving. The full equation is E squared equals mc squared squared plus p times c squared, where p represents the momentum of the object in question. This might all seem a bit confusing, but in fact you can draw it as a right triangle with sides E, mc squared, and p times c, and just use the Pythagorean theorem a squared plus b squared equals c squared to give you the equation. Also, from here it's clear to see that for an object that isn't moving and thus doesn't have any momentum, and thus p is 0, we get back our good old friend E equals mc squared. On the other hand, if the particle in question is massless, like light, then mass is 0, and we get E equals p times c. This tells us that the energy of a massless particle, like a photon of light, is the same as its momentum, up to a factor of the speed of light. In fact, the closer the energy of something is to p times c, the closer that something is to behaving like light. I mean, look here, this tiny little bit of mass is hardly mass at all. Anyway, as an example, an object's velocity is equal to the speed of light times the ratio of the object's momentum to energy, or pc over e. If your momentum increases, p times c gets closer and closer to equaling your energy, so their ratio gets closer and closer to being 1, and your speed gets closer and closer to light speed. But because of that tiny little bit of mass, the momentum side of the triangle will always be a little bit smaller than the energy side. No matter how hard you try to increase your momentum, it never quite gets to the point where p times c equals your energy, and thus your velocity can never quite reach the speed of light, all because the hypotenuse of a right triangle is longer than its legs.
So that one's interesting. I'm going to just put it out there, and you're free to see and look, but you're not required to know the details of that one. What that is later on, we'll probably talk about it a little bit more too, but this E equals mc squared is the non-relativistic version of things. This is energy equals mass times speed of light squared for rest particles, particles at rest. So basically what you started to get into there was the relativistic version of E equals mc squared. And so the amount of energy is different if there's high speeds, right? It becomes noticeable at high speeds anyways. Any speed really, but noticeable at high speeds. And another one here for us.
Let's say Mr. and Mrs. Einstein each have identical relativity clocks. These super accurate timepieces work by bouncing a photon of light between two mirrors a few feet apart. Now, if Albert hurtles past at near the speed of light, Mrs. Einstein would say that his photon has to travel much further between ticks than hers. So, to keep the clocks ticking together, his photon would have to speed up. Except we already know that light doesn't do that. Einstein reasoned that time itself, not light, changes speed.
He simply took this idea seriously, that the speed of light is constant, and that means that the very notion of what space is and what time is, has to give.
So this meant that time itself was no longer absolute, it had to be relative. And this is the big breakthrough that Einstein made.
This fundamental shift in the way we see the universe meant that different clocks could show different times and still be right. Relative to Mrs. Einstein, Albert's clock ticks slower than hers. The faster he goes, the slower it ticks, until at the speed of light, it would stop altogether. Bingo! Einstein had shown how nothing travels faster than light, not even celebrity gossip.
All right, so that analysis shows that time would stop, right? So it's, again, this is one of the explanations that basically you should be familiar with. We're actually going to use that idea of that light clock to develop the equations to do with time dilation in the next lesson. So yeah, it's definitely doable. And here we go for this.
Once upon a time, that magical phrase at the beginning of every good story. But what is the story of time? People say that time flies, that time is money. We waste time. we kill time, we try to save time. But what do we really know about time? Well, like this river, time seems to flow endlessly from one moment to the next. And the flow of time seems to always be in one direction, toward the future. But that may not be right. Discoveries over the last century have shown that much of what we think about time may be nothing more than an illusion. Contrary to everyday experience, time may not flow at all. Our past may not be gone. Our future may already exist. It turns out, time itself can speed up or slow down. And events that we think can unfold in only one direction can also unfold in reverse.
But how could this be? How could we be so wrong about something so familiar? And if time isn't what we all think it is, then what is it? Did it have a beginning? Will it have an end? Where did it come from?
We'd like to corner time as a thing, but it defies that completely by being momentary, by only having definitions that harken back to the notion of time itself.
Time is the thing that everyone knows intimately until you ask them to tell you about it.
What is time is really the $64,000 question to physics.
There's basically no aspect of time which I feel we really fully understand.
So, how do you begin to unlock a mystery as deep and elusive as time? Well, one way is to measure it. And using clocks of all different shapes, sizes, and kinds, we've been measuring time with ever greater accuracy for thousands of years. The first clock was one that you could say ticks just once a day, the rotating Earth. From the repetition of our planet's daily rotation on its axis to its yearly orbit around the sun, we have always used the predictable, consistent motion of the Earth to measure time.
We're always looking for things that repeat over and over again, and that repetition, that cycle of things, forms a clock. That's all time becomes, is some repetitive process.
Measuring the Earth's motion with the sundial, we divided the day into hours.
The Earth rotates once a day, and we tick off the days by looking at the rising and setting of the sun.
With the swing of a pendulum, we divided hours into minutes and seconds. With the vibration of a quartz crystal, we improved accuracy to the thousandths of a second. But the National Institute of Standards and Technology in Colorado is the place to go if you really want to know what time it is.
This is U.S. official time. It doesn't get any more accurate than this.
Here, they measure time with mind-boggling accuracy using one of the smallest objects in the universe, an atom of a rare metal called cesium.
Atoms have a natural frequency, and anything that vibrates, that is giving you repetitive motion, can be a clock. The frequency at which the cesium atom ticks is the official timekeeper for the world.
When a cesium atom is bombarded with energy, it vibrates or ticks, giving off pulses of light over 9 billion times a second.
We count the ticks of the cesium atom, and the cesium atom ticks at this 9,192,631,770 ticks in a second. And so every time you count up to that number, 1 second has gone by. And you get 1 second after 1 second after 1 second after 1 second.
This is just astounding. My watch gains or loses a second every couple of months. We're talking about clocks that would only gain or lose a second in 100 million years.
And that kind of story where we take one measure of time and replace it with something that we decide is more accurate, has been the constant reform process of physics over hundreds of years.
But no matter how accurate our clocks have become, time remains a mystery. Clocks can tell us what time it is, but they haven't been able to tell us what time itself is. What is it we're actually measuring? We may not know what time is, but the experience of the passage of time is a fundamental part of our lives. We're always thinking about time, remembering the past, making plans for the future, living our lives within time's constant tick, tick, tick. I mean, look around any train station, and you can see how time rules our lives. What may not be so obvious is that the rise of train travel played a key role in one of the most startling discoveries about time.
Tickets, please, sir.
Train running on time?
Yes, sir. Thank you.
In the early days of train travel, time posed a unique problem. Back then, each town set their own particular time. Noon was when the sun was directly overhead, more or less. And what time it was in another city, well, that hardly mattered. And to complicate things even further, trains would carry the time of the city where they began their journey. So if I was going from Paris to Geneva, I'd be on Paris time the whole way, since that's where I started. But were I going the other direction, from Geneva to Paris, I'd be on Geneva time.
And as you began to have more and more train lines crossing and more different times located at that interchange, it became a nightmare of confusion.
The need to coordinate clocks over great distances became a huge issue, especially when the cities were connected by a single track. And here's where the modern story of time begins. As the need for synchronized clocks became ever more critical, a young physicist named Albert Einstein took a job at the patent office in Bern, Switzerland.
It was a ringside seat to all of the great inventions of the time. The patents showed how new and exciting ways to synchronize clocks with the exchange of telegraph signals, clocks that were synchronized by radio waves, all made the synchronization of time and what time was and how it was measured something immediately important and exciting for Einstein.
Einstein would soon shake up the world with a radical insight into the nature of time. And these mechanical devices provided unexpected inspiration. Einstein realized that these attempts to synchronize clocks, they were much more than merely creative inventions. Instead, he realized that they were revealing a deep crack in our understanding of time itself. Most people view time in a pretty simple, straightforward way. Time ticks the same for everyone, everywhere. It's a common sense picture established by the father of modern science, Isaac Newton.
time for Isaac Newton is something that is an immutable property of the universe. Time always changes at the same rate.
Time just goes along, and there's really nothing we can do about it.
Sensible as Newton's picture of time may seem, Einstein realized it wasn't right. He discovered that time could run at different rates. Strange as it sounds, this means that time for me may not be the same as time for you. Einstein's discovery smashed Newton's conception of reality.
Einstein says that time is not just a label on the whole universe. Time is experienced individually.
What Einstein gave us is a much, much richer picture where everybody has their own private time, which runs at their own private rate.
There isn't time in the sense of a universal tick-tock. There were times.
Einstein came to this shocking revelation by uncovering a hidden connection between space and time. What Einstein figured out is that there's a profound link between motion through space and the passage of time. Roughly speaking.
All right, and that's what we've talked about in the past about the speed of light and how it's connects distance and time and so on, right? So, quick recap: you've looked at investigating if light was a particle or wave, and that led to quantum theory, quantum mechanics, right? Versus now we're looking at things increasing speed and getting to the close to the speed of light. And so we learned that the speed of light is not relative. In other words, everybody sees it at going that particular speed. And so like the consequences we're talking about rate of time, passing, and so on. Again, special relativity consequences of this fact about light, right? And so just to try and keep reminding you of where this is coming from, this is a diagram to do with that Michelson-Morley experiment that shined a laser, and it was a beam splitter, and the beam would go this way and that and up, and then it would go this way and up and up. And so the two beams that arrive actually started this way and that way, whatever, anyways, right? So the beam splitter makes it so they arrive at a certain on a screen, and if there's a difference in the path length because of wind that it's traveling upstream and downstream in, there'd be a certain interference pattern, and that interference pattern was never observed to change depending on the angle of the experiment. So that was the conclusion. The conclusion was, of course, that light isn't relative to anything. It's just always light speed. And there's other experiments and ideas as well, but that's the key one you'll always hear about, the Michelson-Morley experiment. So observations of light coming from the stars, for example, the stars are moving towards or away from us or whatever, and there's no difference found, right? The Doppler shift of light, just like in the sound unit in grade 11, the frequency and wavelength change because of the speed of the emitter of the wave. It's never found to be the case, right? The differences, the speed of light is exactly the same, of course, regardless of all velocities and so on. And so water waves approaching us from boats, at different speeds and so on, if the water's moving at a different speed or whatever you want to think of it as, the speeds would change depending on the velocity of the medium more so there. But it's not true for light, right? And so this is what we talked about, how Einstein realized, right? In the video it says, Einstein realized that if there's something weird going on to do with velocity, then there has to be something weird going on to do with distance and time, right? So Einstein noticed this and accepted it, whereas other scientists were focused on ways of getting around it, proving it not to be true or whatever. Didn't lean into it like Einstein did. And so, like we said, we've already concluded about light speed being the ultimate speed. And what did we have here? That was just a picture of that spaceship thing, right? And that's just the conclusion of that, so I won't bother talking about that much. So things are also strange if the ship was going, really fast, right? The observer would, two different observers would say it happened quickly and happened slowly. But of course, this is strange, but it is in fact what each observer would see. Yeah. All right. So the spaceship example shows the next consequence. We're looking at about the idea of two things happening at the same time, or simultaneity. not being a concrete concept. It's relative, which means it depends on your velocities. And so I'm just going to read for us here. It says, with minimal effort, we can make use of the constancy of the speed of light to show that familiar everyday conception of time is plain wrong. Imagine that the leaders of two warring nations, his analogies are always really strange, are sitting at opposite ends of a long negotiating table and just have concluded an agreement for a ceasefire. But neither wants to sign the accord before the other. Secretary General of the United Nations comes up with a brilliant solution. A light bulb, initially turned off, will be placed midway between the two presidents. When it's turned on, the light will reach each of the presidents simultaneously, and since they are equidistant from the bulb, each president agrees to sign a copy of the accord when he or she sees it. And so the plan is carried out, and the agreement is signed to the satisfaction of both sides. Both nations are happy. No one signed it first, right? Flushed with success, the Secretary General makes use of the same approach with two other embattled nations that have also reached a peace agreement. The only difference is the presidents involved in this negotiation are sitting at opposite ends of a table inside a train traveling along at a constant velocity. Fittingly, the president of forward land is facing in the direction of the train's motion, while the president of backward land is facing in the opposite direction. Familiar with the fact that the laws of physics take precisely the same form regardless of one's state of motion, so long as the motion is unchanging, the Secretary General takes no heed of this difference, doesn't think it would make a difference, and carries out the light bulb initiated signing ceremony as before. Both presidents sign the agreement, and along with their entourage of advisors, they celebrate the end of hostilities. They all agree that they signed at the same time. On the train from both sides, they agree that it was signed simultaneously, and so page here. There we go. I missed the paragraph. Just then, word arrives that fighting has broken out between the people from each country who had been watching the signing ceremony from the platform outside the moving train. All those on the negotiation train are dismayed to hear that the reason for the renewed hostilities is the claim by people from forward land that they've been duped, as their president signed the agreement before the president of backward land. Apparently that matters for some reason, right? So as everyone on the train from both sides agrees that it was signed simultaneously, how can it be the outside observers watching think otherwise? How could they have seen otherwise? Let's consider in more detail the perspective of an observer on the platform. Initially, the bulb on the train is dark. Then, at a particular moment when it illuminates, sending beams of light speeding towards both presidents, from the perspective of the person on the platform, the president of forward land is heading toward the emitted light, while the president of backward land is retreating. This means to the platform observers that the light beam does not travel as far to reach the president of forward land, who moves toward the approaching light, as it does to reach the president of backward land, who moves away from it. This is not a statement about the speed of light as it travels toward the two presidents. We've already noted that regardless of the state of motion of the source or the observer, the speed of light is always going to be the same. Instead, we are describing only how far. From the vantage point of platform observers, the initial flash of light must travel to reach to each of the presidents. Since this distance is less for the president of forward land than it is for the president of backward land, and since the speed of light towards each is the same from any observer, the speed of light will reach president of forward land first. This is why the citizens of forward land claim to have been duped. When CNN broadcasts the eyewitness account, the Secretary General, two presidents, and all of the advisors can't believe their ears. They all agree that the light bulb was secured firmly exactly midway between the two presidents, and that therefore, without further ado, light emitted traveled the same distance from each, the middle of the table out to each edge, to each of them. Since light speed emitted to the left and the right is the same, they believe, and in fact observed, saw with their very own eyes in person, that the light clearly reached each president simultaneously. Who is right? That those on or off the train. The observations of each group and their supporting explanations are impeccable. The answer is actually that both are right. Like our two space inhabitants, George and Gracie, each perspective is an equal claim on the truth. The only subtlety here is that the perspective truths seem to be contradictory. An important political issue is at stake. Did the president sign the agreement simultaneously? The observations and reasoning above ineluctably lead us to the conclusion that according to those on the train, they did sign simultaneously, and according to those on the platform, they did not. In other words, two things that are simultaneous from the viewpoint of some observers will not be simultaneous from the viewpoint of other observers if the two groups are in relative motion. It's a startling conclusion. It is one of the deepest insights into the nature of reality ever discovered. Nevertheless, if long after you set this book down, you remember nothing of this chapter except for the ill-fated attempt to taunt, whatever, I don't know how to pronounce, you'll have retained the essence of Einstein's discovery. Without highbrow mathematics or convoluted chain of logic, this completely unexpected feature of time follows directly from the constancy of speed of light, as the scenario illustrates. A lot of physics ideas, concepts, discoveries are based on very complicated calculations, right? Whereas this one's not at all. Notice that if the speed of light were not constant, but behaved according to our intuition based on slow-moving baseballs and snowballs, the platform observers would agree with those on the train. A platform observer would still claim that the photons have to travel farther to reach the present or backward land than they do to reach the present forward land. However, as usual, intuition would apply. The light approaching the present or backward land would be moving more quickly, since it would have received a kick from the forward-moving train. Similarly, observers would see that the light approaching the present and forward land would be moving more slowly, having been dragged back by the train's motion. When these erroneous, not true for light, right, effects were considered, the observers on the platform would see that the light beams reached each present simultaneously. However, in the real world, light does not speed up or slow down. It cannot be kicked to a higher speed or dragged to a slower one. Platform observers will therefore justifiably claim and see, they would see the light reach the present of forward land first. The constancy of the speed of light requires us to give up the age-old notion that simultaneity is a universal concept that everyone, regardless of their state of motion, agrees upon. The universal clock, previously envisioned to dispassionately tick off identical seconds here on Earth and on Mars and on Jupiter and in the Andromeda Galaxy, and each and every nook and cranny of the cosmos does not exist. On the contrary, observers in relative motion will not agree on which events occur at the same time. Once again, the reason that this conclusion, a bona fide characteristic of the world we inhabit, is so unfamiliar is that the effects are extremely small when the speeds involved are those commonly encountered in everyday experience. If the negotiating table were 100 feet long and the train were moving at 10 miles per hour, observers would see the light beam reach the present and forward land about a millionth of a billionth of a second before it reached the present and backward land. Although this represents a genuine difference, it is of course so tiny it cannot be detected by human senses. If the train were moving considerably faster, say at 600 million miles per hour, from the perspective of someone on the platform, the light would take almost 20 times as long to reach the present or backward land compared to the time to reach the present or forward land. At high speeds, the startling effects of special relativity become increasingly pronounced. So, our conclusion, simultaneity. Two events that are simultaneous, as observed from one reference frame, are not, right? Will not be simultaneous if observed from another reference frame that is in relative motion. Again, it's a consequence of the speed of light being constant and observed to be the same from all observers. Okay, so visuals of this here for us, the light traveling each distance and so on, right? So light's observed to travel the same distance and get there simultaneously, but in the other case here, the train moves a distance delta x, right? And so the light has to travel farther to get to that person at the front and so on, right? And so it's traveling farther, but of course the speed would be observed to be light speed the whole time. We got C's everywhere, right? No matter whether this person's observing or whether people in here are observing, right? The speed of light is the same. So it is messed up. Since all observers see light traveling at exactly 300 million per second, and so on, right? So, yeah, covered that enough, right? Yeah, all the same stuff, just written down in case you want to look it over later or whatever. Yeah, so two events that are simultaneous will not be simultaneous, right? Both of the observations are true. This is what would be observed from each reference frame. It's just how it is. And the first postulate of special relativity points out that there is no such thing as absolute motion or simultaneity as a result, right? Both reference frames have all laws of physics equally valid. Neither can be thought of as really moving or stationary. Each give equally valid observations, and events observed as being simultaneous from one reference frame will not be simultaneous from another. So yeah, a little weird. Clearly, the fact that the speed of light is constant and the same regardless of the observer's reference frame, velocity, and so on is having some surprising effects on our concept of time. Simultaneity is not concrete and absolute as we naturally think. And so, yeah, next we're going to see more strange consequences about time itself and length and mass and so on. All right, so that is your next bit about special relativity. Just 3 little questions there to thinking questions, no math, which is kind of nice, a little break from that. And yeah, if you have any questions, let me know. Thank you.